Welcome back to Play-by-Play Chemistry Regents exam. We examine Part B1 of the June 2014 Chemistry Regents exam. Part B1 is typically 20 multiple choice questions, and where Part A is more about vocabulary, as you saw, very heavy with the vocabulary, Part B1 is more mathy. There's still vocabulary, but there's more mathy, there's more reference tables, and there's more kind of critical thinking, you know, trying to put things together, make connections. Whereas Part A was mostly just, it's on the reference table. It's still going to be on the reference tables, but they're going to be slightly more complex questions. Interestingly enough, because there's not as much vocabulary, I found that people tend to do better on Part B1 than they do on Part A, which is weird. Know your vocabulary. Part A is easy, dead easy if you know your vocabulary. And Part B1 is not that bad either. Let's have a look at it. Question 31. Which notations represent different isotopes of the element sodium? Well, we've got two things going on here. We've got sulfur, we've got sodium. And how do we know S is sulfur and not sodium? Because that's one of the most commonly made mistakes that you see. If you're not sure about the name of the element, and even if you are sure, it definitely pays to double check. Go to reference table S, and it will tell you without any hesitation that sodium is Na and that sulfur is S. So don't make that mistake. It ain't sulfur. Now we need different isotopes. Now what is an isotope? Isotopes are atoms of the same element that have different atomic mass. And the reason they have different atomic mass is because they have a different number of neutrons. Choice 3, this tells us charge. These would represent two different species of sodium. A sodium ion and a neutral sodium atom. That would be species. That's useful if you're doing half reactions. Isotopes are the same element with different mass. Number 32. Which electron configuration represents the electrons in an atom of gallium in the excited state? How the heck are we supposed to know? Let's look it up. Gallium has a ground state configuration of 2-8-18-3 for a total of 31 electrons. So what we need is 31 electrons, but not in that order. One of the electrons lower down is boosted up to a higher energy level. 2 plus 18 plus 17 plus 3. Well, that's 20, 28, 30. This adds up to 30. Gallium has 31 electrons, not 30. Choice 2. 2-8 is 10, 27, 31. Gallium has 31 electrons. This could be a choice. 2 plus 8 plus 18 plus 3. Well, this adds up to 10, 28, 31. This adds up to 31. That works, potentially. 2 plus 8 is 10, plus 18 is 28, plus 4 is 32, not 31. Say goodbye to choice 4. Now, it says in the excited state. Remember, the configuration given here is the ground state configuration. 2, 8, 18, 3. 2, 8, 18, 3. We want the excited state. That's the ground state. Hello, you win. One of these 18 electrons was boosted up to the next higher energy level. Number 33. Which statement describes the general trends in electronegativity and first ionization energy as the elements in period 3 are considered in order from sodium to chlorine? Now, you could memorize the trends and remember that metals have low electronegativity and nonmetals have high electronegativity, and that electronegativity and ionization energy are directly related to each other, so that electronegativity will increase and with it ionization energy. So you could definitely do that, and electronegativity and first ionization energy both increase. That's the choice. But what if you didn't remember that? Well, fortunately, there's a reference table. Reference table S gives you the first ionization energy and electronegativity for all these different elements. Sodium has an electronegativity of 0.9. Chlorine's is 3.2, so obviously electronegativity increases. First ionization energy for sodium is 496. For chlorine, it's 1251. That's a heck of a boost. And you can see the trend is an upwards trend. So both ionization energy and electronegativity increase as you go from sodium to chlorine. So don't guess, go to S. Number 34, what is the gram formula mass of iron 3 nitrate? Well, there's no need to guess this either. Gram formula mass, also known as molar mass, is simply the sum of the atomic masses of each element in the compound. Now, in my class, I teach the students that the atomic mass is rounded to the nearest tenth. So that's what I'll show you. Iron, of which there is 1, has a mass of 55.8 grams per mole. 55.8. Plus, we have 3 nitrogens. Each nitrogen has a mass of 14. 3 of them would have a mass of 42. So far, our gram formula mass is up to 97.8, but we have to add to it the 9 oxygens in the compound. 3 times 3 is 9, and each oxygen has a mass of 16.0. 9 of them would be 144, giving us a total gram formula mass of 241.8 grams per mole. Now the choices that are given here are rounded to the nearest whole number. Well, 241.8 to the nearest whole number, 242 grams per mole. The standards say that formula mass should be taken to the tenths place, but the Regents does not always comply with that. 35. Given the balanced equation representing the reaction, aluminum sulfate plus 6 sodium hydroxides forms 2 aluminum hydroxides plus 3 sodium sulfates. The mole ratio of sodium hydroxide to aluminum hydroxide is, well, here's the mole ratio right here. The coefficients give you the mole ratio. It's a 6:2 ratio. Oh, 6:2. Can we simplify that? Because 6:2 is not one of the choices. What does 6:2 simplify? Oh, 3:1. It's a 3:1 ratio of sodium hydroxide to aluminum hydroxide. There you go. Number 36. Which equation represents a single replacement reaction? The first question has a compound breaking up into simpler substances. This would be called decomposition. Decomposition is not single replacement, ergo, you go. Number 2, 2 elements combine to form a compound. That's not single replacement, it's synthesis. See ya. Choice 3, the magnesium replaces hydrogen to form magnesium sulfate. That is single replacement. Winner. Why not choice 4? K replaces H, OH replaces, you know what? We got a double replacement reaction here, where the H and the K are switching places. This, ladies and gentlemen, would be an example of a double replacement reaction. You know what? Double replacement? That ain't single replacement. So long. See ya, choice 3. Number 37. The accepted value for the percent by mass of water in a hydrate is 36.0%. In a laboratory activity, a student determines the percent by mass of water in the hydrate to be 37.8%. What is the percent error for the student's measured value? How am I supposed to know that? Jeez. What, I think I am a teacher or something? Okay. Look at that. Look at that. No, you can't see that. No, that's better. You can see that now. Percent error is equal to measured value minus accepted value, and it's actually an absolute value, so there's no negative sign involved with it. Divided by accepted value times 100. Measured minus accepted over accepted times 100. The accepted value is 36%. That's what goes on the bottom, 36.0%. I'm going to multiply that by 100 when we're done. And since it's measured minus accepted, minus 36.0. A student determined the percent by composition of the water of a hydrate to be 37.8%. That's our experimental value, 37.8. Now if we subtract that, we get 1.8, which we can then divide by 36, and then we can multiply that by 100 to get a percent, 5% error. Choice 1. Now, if you forgot to multiply by 100, you'd probably get choice 4. Don't forget to multiply by 100. It tells you to do that right here. Here, anyway, see, multiply by 100, barely see it. No, there we go, times 100. Okay. Number 38. The boiling points at standard pressure of 4 compounds are given in the table below. So we got these 4 compounds here. Here are their boiling points. Water boils at the highest temperature, and this boils at the lowest. No, this doesn't boil at the lowest. That boils at the lowest. Hydrogen sulfide. Okay. Which type of attraction can be used to explain the unusually high boiling point of water? Now, you may have heard terms over the course of the year like van der Waals forces, or London dispersion forces, or dipole attraction. But there's only one type of attractive force that the Regents is going to ask you by name. The only one you're responsible for is hydrogen bonding. Now, why is it not the others? Well, first of all, ionic bonding is a type of attraction. It's the attraction of a positive ion for a negative ion. But that's metal to non-metal. We got all non-metals here, so, well, actually we have some metalloids going on here too. But same thing, covalent, not ionic. Not ionic. Why is it not covalent bonds? Because it's not asking what holds the hydrogen and oxygen together in the compound. It's saying the force of attraction that can be used to explain the unusually high boiling point of water. So what does it mean to boil water? When you boil water, molecules of water, separate molecules, go their own separate ways. The molecules themselves don't break up any further, but the molecules will separate from each other. Now, why do they do this? Well, water is a highly polar molecule. It's got one line of symmetry, and that line of symmetry points towards oxygen, which would be the partially negative end. Hydrogen would be the partially positive end. So the partially negative end, the oxygen end of one molecule, will attract to the partially positive hydrogen end of another. And we call that attractive force between the H end of one molecule and the nitrogen, oxygen, or fluorine end of another molecule. We call that attractive force hydrogen bonding. It's the only kind of attractive force that you're going to be responsible for knowing the name of. (39). Which formula represents a molecule with the most polar bond? That's a very interesting question. In polar molecules, we're dealing with lines of symmetry. When we're dealing with bonds, we're looking at the electronegativity difference between the bonded atoms. And fortunately, we can look up the electronegativities of each element. We have carbon, oxygen, nitrogen. Let's start with that. Carbon is 2.6, nitrogen is 3.0, oxygen is 3.4, hydrogen is 2.2, and chlorine is 3.2. and iodine is 2.7. So let's subtract these numbers. 3.6 minus 3.4 is 0.2. 3.2 minus 3.4, 0.2. 2.2 minus 2.7, well, that would be 0.5 difference. And then 3.2 and 2.2, 1.0 difference. The most polar bond is the one with the highest electronegativity difference. HCl has the most polar covalent bond of any in the rest of the choices. Question 40. The graph below represents the uniform heating of a substance from the solid to the gas phase. Solid, melting. Liquid, boiling, gas. Which line represents boiling? Well, during a phase change, temperature remains constant until the phase change is complete. The lower phase change, the lower temperature, would be melting. The phase change at the higher temperature would be boiling. Boiling would be the higher phase change temperature, DE. During AB, it's a solid. During CD, it's a liquid. During EF, it's a gas. It's melting and it's boiling under those two circumstances. 41. A 1 gram sample of a compound is added to 100 grams of water and the resulting mixture is then thoroughly stirred. Some of the compound is then separated from the mixture by filtration. Based on Table F, the compound could be. Well, Table F has your solubility guidelines. Basically, it tells you which things are soluble, which will be over on this side here, and which things are, well, let's back this up a little bit. Reference Table F gives you your solubility guidelines. Anything on this side? Well, that would be soluble, except when combined with these guys. And over here, these are insoluble, except when combined with these guys. Now, solutions cannot be separated by filtering. So if anything is separated in the filtering process, it must be a solid precipitate. Precipitate, it means that it is not soluble and can be filtered out. So let's see what we've got as choices. AgCl, CaCl2, NaCl, and NiCl2. They are all chlorides. Now, according to this table, chlorides are soluble, except when combined with silver, lead, or dimercury 1. So what does that mean? Silver, lead, mercury, silver. That is the only insoluble one of the bunch, and it can be separated by filtering. Number 42. At standard pressure, the total amount of heat required to completely vaporize a 100 gram sample of water at its boiling point. Vaporize. 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 Where have we heard that before? Oh, look at that. What's that? It's called heat of vaporization. It's the amount of heat it takes to vaporize a liquid. And it's 2,260 joules per gram. Well, what do we do with that? Well, on Table T, it tells us that we take that heat of vaporization and we multiply it by the mass of the water or liquid we're trying to vaporize. It's water because it's 2260. And that'll give us our quantity of heat. So mass times heat of vaporization. So our mass is 100 grams. Let's move that in there. Our mass is 100 grams. So we have 100 grams, which we will multiply by 2,260 joules per gram. That gives us 226,000. But that's not one of our choices. All of our choices are given to us in scientific notation. So let's see. After the 2, there's 1, 2, 3, 4, 5 places. So it's 10 to the 5th. 2.26 times 10 to the 5th joules. Question 43. A sample of helium gas in a sealed rigid container. That means nothing can get in, nothing can get out. Can't change the volume either because it's rigid. You can't like squish it. What occurs as the temperature of the sample is increased? So we're looking at temperature versus mass, moles, volume, or frequency of collisions. What occurs as the temperature increases? Now, it's a sealed container. That means that no gas can get out. That means there's still going to be the same amount of gas in there. Mass decreases? No. Mass remains the same because none of the gas is able to get out. It's a sealed container. The number of moles of gas, well, same thing. You're going to have the same number of molecules of gas because it's a sealed container. The volume decreases. Well, it's a rigid container. That means the sides can't like expand or contract. It's solid. So the volume can't change. And besides, if you increase the temperature, if you could change the volume, it would increase. So that rules that out. However, you will get more collisions. Why? Because when you increase the temperature, the molecules move faster, which means they'll be able to hit each other more frequently and harder, increasing the number of effective collisions between atoms. That's from your kinetics unit. Number 44. Given the equation representing a reaction, 2 sulfur dioxides plus oxygen forms an equilibrium with 2 sulfur trioxide gas plus heat, what change causes the equilibrium to shift to the right? This is a Le Chatelier's principle problem. The way it works is equilibrium shifts away from what you add. This will bring its concentration back down so that you can undo your stress. Equilibrium will shift away, will shift towards whatever you remove. And this will make more of whatever you remove to bring its concentration back up again. So let's see, what change causes the equilibrium to shift to the right? Adding a catalyst. Well, catalysts lower the activation energy, which affects both the forward and reverse reaction rates equally. Catalysts do not affect systems at equilibrium. Adding more oxygen. Oh, there we go. If we increase a reactant, we'll need to shift to the product side to use it up. It also increases the number of collisions between these two, making the forward rate faster than the reverse rate. So why is it not 3? Decreasing the pressure. Well, decreasing the pressure, the equilibrium is going to try to bring the pressure back up by shifting to the side that has more gas. The left side has 3 moles of gas, the right side has only 2. So if you decrease the pressure, it will shift to the right to bring the pressure back up. So it's not 3. Increasing temperature. Well, increasing temperature will cause it to shift in an increasing the temperature will cause it to shift in an endothermic direction to bring the temperature back down to convert that excess kinetic energy into potential energy. Look what side heat is on. The endothermic direction is in that direction. So increasing the temperature will also cause it to shift to the left. So the only one that makes it go to the right, adding more oxygen. You could have also added sulfur dioxide. You could remove SO3, lower the pressure, or lower the temperature. And any of those would have made it shift to the right. Number 45. Number 45, given the formula representing this compound, what is the chemical name of the compound? Well, it has 1, 2, 3, 4, 5 carbons, so it's pent. They all have pent. Okay, that doesn't help. Okay, is there anything distinguishing about this? Well, there's a double bond here. Okay, if it's got a double bond, I know I've seen this before, a double bond between carbons in a hydrocarbon makes it an alkene, which means the ending will be -ene. So it's either 3-pentene or 2-pentene. Now, where do we get the number from? How many carbons in before we reach the double bond? Well, going in this direction, 1, 2, 3 carbons. 3 pentene? Not so fast. Going from this direction, you only have to go 2 carbons. And the IUPAC rules, the International Union of Pure and Applied Chemistry, yes, that's what IUPAC means. It just means the standard naming system says you start counting from the side the double bond is closest to. 2 pentene. 46. What is the oxidation number of manganese in potassium permanganate? This is a nifty one. KMnO4. According to the periodic table, manganese can have many different charges. Manganese can be +2, manganese can be +2, +3, +4, or even +7. So which of these charges is it? Well, potassium can only be +1. And oxygen, -2. So with that information, potassium +1, oxygen -2, in a compound, all the charges add up to 0. Now, we have 1 potassium, which contributes +1 towards that goal. We have 4 oxygens, each of which is -2. So oxygen contributes 4 times 2, -8 towards that goal of adding up to 0. So what does manganese have to be? Well, we've got -8 and +1. The negatives are winning, so manganese has to be positive. -8 +1 and +7. And there's only 1 manganese, so that's the charge of the manganese, +7. There's your answer. 47. When the pH of an aqueous solution is changed from 1 to 2, now that means pH is going up. That means it's less acid and more base. And it's going up by 1. Now, a pH value is based on powers of 10. If you change the pH by 1, that is a 10-fold change. If you change the pH by 2, that's a 10 to the second or 100-fold change. If you change the pH by 3, that's a 10 to the third or 1,000-fold change. Well, we're only changing by 1, from 1 to 2. So therefore, a factor of 10. It's either choice 2 or 4. Now, as far as increased or decreased is concerned, it's the next part of the question. The concentration of hydronium ion. Well, what is hydronium? The hydronium ion, H3O+, this is what you'll find in an acid, as opposed to hydroxide, OH-, which is what you would find in a base. So what this question is saying, because it's talking about hydronium, it's talking about it being an acid. And we already know it's less acidic. That means that it's going to be a weaker acid. The concentration of hydronium decreases by a factor of 10. Because a pH of 2 is 10 times weaker than a pH of 1, as far as being an acid is concerned. Number 48. What is the color of the indicator thymol blue in a solution that has a pH of 11? How the heck are you supposed to know? That's not something you're going to be able to pull off the top of your head. Instead, use the reference table for acid-base indicators. Now our question is asking about thymol blue in a pH of 11. Thymol blue is yellow under a pH of 8, so pH of 1, 2, 3, 4, 5, 6, 7, it's yellow. Above 9.6, pH of 11 would qualify as being above 9.6, it's blue. So for a pH of 10, 11, 12, 13, 14, all the way, it's blue. What is it in the middle? Doesn't tell you. It doesn't tell you. So therefore you would not be responsible for it. You only need to know the color below the range and above the range. In this range, the color is transitioning from yellow to blue. At a pH of 11, it's firmly in the blue range. 49. Which formula represents compounds that are isomers of each other? The definition of isomer is the same molecular formula, but different structural formula. In other words, if I count up the number of carbons and hydrogens and oxygens, they should be the same, but their structures should be different. In other words, they should have the same number of carbons, hydrogens, and/or oxygens, and yet be named differently. This is methane, this is ethane. They are named differently. This is CH4, this is C2H6. Yeah, not isomers. This is C3H8O. C3H8O. This is C3H, 1, 2, 3, 4, 5, 6, 7, 8, looking good, and there's one oxygen. Now, are they isomers? Here, this is 1-propanol. This is methyl ethyl ether. They're named differently. Those are your isomers. Well, why are the rest of them not isomers? Well, this is CH4O, and this is CH4O. But they're the same molecule. This is methanol, that's also methanol. So they're not isomers. What about choice 4? Well, this has 3 carbons and that has 2 carbons. So right there, that just sort of puts the kibosh on that. Same molecular formula, different structural formula. That's what an isomer is all about. And finally, question number 50. Radioisotopes have all kinds of uses. Neutralizations of acid spills are not among them. Bases can be used for those. Decreasing dissolved oxygen level in seawater? Well, how the heck are the fish gonna breathe? It's not exactly beneficial, which means good or helpful use. Decreasing dissolved oxygen level in seawater? I don't know what radioisotopes are gonna do there. That's not beneficial anyway. Increasing the concentration of carbon dioxide in the atmosphere? Yeah, we're already above 400 parts per million and the global temperature's been rising. The vast, overwhelming majority of scientific consensus is that putting extra carbon dioxide in the atmosphere is the least beneficial thing imaginable. One beneficial, good use of radioactive isotopes, iodine-131 can be used to treat thyroid problems, specifically hyperthyroidism. Cobalt-60 can be used for radiation treatment of brain tumors, and technetium-99 can be used to detect brain tumors. Detection of disease. Now, as you can see in part B, there's really not a lot of memorization. Basically, you just have to know where the reference tables are and how to use them. There's still some vocabulary you need to know, but just memorization of basic facts, there's not a lot of that. If you know your vocabulary and you know your reference tables, and you meticulously deal with each question, eliminating choices as you go, writing down what certain words mean to help you, you can really do well on Part A and B1. And that's the key to doing really well on the Regents exam.